Hello, I'm Mr. McBrien. This is TEJ20, representing text with binary numbers. Ontario would like for us to be able to describe how computers represent and process data, including ASCII code, and that's what we'll talk about today. So by way of introduction, I'd invite you to think about the idea. Think about what's on your computer today, and it doesn't matter whether your computer is an iPad, a phone, Windows 10, an iMac, what have you. I'd invite you to think about what is on your computer. You can pause the video for a second and think about what your answer would be to that. Now, chances are, you said, I've got videos, I've got documents, I've got presentations, pictures, these kinds of things, and music. And that answer is true. That is accurate. And we think of a hard drive or a flash drive as containing documents, pictures, videos, and all these things. But in truth, at its most fundamental, it contains zeros and ones. And we won't worry about converting zeros and ones to pictures or movies or sound right now. Let's just focus on the idea of a document and how text is encoded into zeros and ones. It's not as simple as it sounds. And similarly, we can ask ourselves, how does a keyboard convert a key press into ones and zeros? Because it's the same problem in essence. So, for fun, here's a joke. And the joke doesn't seem that funny because the joke is only funny to a computer. It's only interesting to a computer. Why? Because it's written in binary. But the majority of the information we'll talk about today is all tied up in understanding this joke. So today we're going to learn how to decipher a joke that's been written in binary. Okay, so do you remember how hard drives store information physically? Remember, it's a series of tiny magnets that either have ones or zeros in them, right? So how do we store text with zeros and ones? Now you might be tempted to say, well, it's just like converting binary to decimal. But no, there's no mathematical way to convert a 0 or a 1 into an A or a B. So when we have to do that, we have to do it in a different way. We can't just do it mathematically. So before we go any further, we can ask ourselves the question, are there other ways to encode text? And the answer is yes. You may have heard of Morse code before. In Morse code, characters are converted into a series of dots or dashes with spaces in between. For example, an S is 3 dots, an O is 3 dashes. So SOS, the universal call for help, would be ... dash 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 ... Let's see if I can do it with the microphone. All right, well, that'll be an interesting experiment to see how that sounds on the video. In any case, we have a way to encode letters into simple data pieces. Now, is this a binary language? You can argue it is, and with some careful collation, it could be. But in fact, it's more than that. If you notice, we've got 3 kinds of data that can go in there. We can have the dots and the dashes, but we also need to have a space in between. And so another way of looking at this is a 0, a 1, and a 2 that are available to us in our encryption. So we can't use simple Morse code. Having said that, Morse code is very efficient in terms of time, and we don't need that level of efficiency. So we'll take a different kind of approach to it. We need more than 3 characters, like 3 dots or 3 dashes, to encode our text. We also need to have punctuation, spaces, and capitals, and more things. So we need to be a bit more complicated than Morse code. We can't use it directly. Now, in fact, you could imagine a simple lookup table, and that was what existed in the early days of computers. So IBM had a 6-bit code that would allow them to encode most bits of text. And they didn't want to move away from this. They had set the standard for the PC, and they didn't want to move away from that 6-bit code. But many people were noting that it just wasn't elaborate enough to be able to encode all the text that someone might need. Now, no other single company had a large enough market to just go it on their own and just say, this will be the new standard. So a coalition was formed between people who created computers, peripherals, and people who were in charge of data transmission. And they formed the ASCII, American Standard Code for Information Interchange, that instead of 6 bits, used 7 bits. So it wasn't quite as efficient, but it allowed for 128 different characters, which was a dramatic improvement over the 64 characters you could have from a 6-bit code. Now, in fact, some equipment had already reserved the 0000, 7-bit 0, or the 128. So 0 and 128, they considered those to be forbidden. So they were able to do 126 different characters. And this is the lookup table that they designed. So based on this, you could take binary numbers and you could pull out given characters, including anything from the keyboard and a few more things, like a line feed and a carriage return and stuff like this. So the good news is there are lookup tables online, so you can go ahead and you do not need to memorize this thing. You can look things up yourself. In any tests in our course, you'll be given a lookup table. Now, 7 bits might seem to make sense, but in fact, it became clear that a bit more was needed. So after ASCII was created, it was decided to use a complete byte to encode a character, or 8 bits. And in fact, almost always today, ASCII will be an 8-bit character rather than a 7-bit character. But all of those additional 128 characters that aren't covered under the 7-bit pattern are non-standard. So all these other ones were never defined by the ASCII coalition. And we call those extended ASCII codes. And all of them start with a 1 as their first bit. And they may mean something different depending on the manufacturer and the equipment. So some of you may be quite sharp and have realized that hexadecimal is not a required piece of information for grade 10 computer technology. We in fact learned hexadecimal specifically because it makes it so much easier to accurately convert ASCII characters. So we'll talk about hexadecimal a fair bit, and before you spend too much time on these slides, make sure you have a reasonable understanding of hexadecimal and conversion from binary to hexadecimal. So there are some patterns that you can see in the in ASCII, like the first 32 patterns written in hexadecimal. That means anything starting with a 1 or a 0 are control codes, including line feed and carriage return. So anything starting with a 2 are special characters. Then you have numbers, capital letters, lowercase letters. So you can see these patterns, and you can certainly decipher those if you look through the lookup tables that have been provided. Now, in terms of a sample problem, when you try to decode a string such as this one, at first it can look really scary. So what you want to do here is you want to make sure, notice that the spaces are very useful here. You want to make sure that you take each one of these binary strings and convert it into its hex first. So how do you do that? You take 4 bits and convert that 4 bits into a hex character. And you can either memorize those things. We've already covered how to convert binary to hex. So when you go to decode that bit stream, a given bit stream of any kind, you want to break it into groups of 8. Rewrite as a series of pairs of hexadecimal digits. So our groups of 8 in this case, notice that the bit stream continues, represented by the ... So we break it into groups of 8. So in this case, we're only going to decipher 4 characters. So the first 4 bits give us a 5. The next 4 bits give us a 4, a 6, then an 8. Remember, this is all in hex, right? So it's very easy to convert. A 6 and a 5, a 2 and a 0, and then we don't have enough of the bits remaining to get to the next character. So we only have 4 characters here. Now, it is very common to see the bit stream already represented in pairs of hex digits. So that byte is a 2-digit hex character. We'll often look at binary just as an important exercise for better understanding of these things. So then we have our problem. We can go to our lookup table, right, and pull out given characters from our lookup table. Remember, the lowercase h indicates that it's a hexadecimal number. So capital A is 41. Capital B is 42 in hex, capital C is 43 in hex, and so on and so on. Okay, and line feed and carriage return and things like this. So our original stream, the long stream that I first presented you, I've converted it into hex here. 5-4, 6-8, 6-5, 2-0, 3-3, 0A, 0D, and so on. We can go to the hex table and we convert that to text. Capital T is 54, lowercase h 6-8, 2-0 is a space, 3-3 is the number 3, and then OAOD is line feed carriage return. Finally, 4-7 is capital G, 6F is O, A, T, S. Remember, you'll be responsible for whether it's capital or not. So that original binary string converted into the 3, return, capital G goats. Now, I included that line feed carriage return concept because it is kind of important. Unfortunately, different operating systems use different standards for indicating end of line. Microsoft uses that 2-character sequence we saw there, carriage return line feed. Unix only uses the carriage return, and oddly, Apple uses the line feed. Now what this means, you may have seen in some cases, if you're a programmer, you may have seen instances where moving text from one system to another causes problems. This is a fact of life for programmers today, and certainly moving between different operating systems, this would not be the This would not be the most significant problem, but it is a problem moving information from one system to another. Okay, so that's enough, I think, for today. We need to always remember in everything we do that computers store information in binary form, in zeros and ones. In order to store text on computers, we have to convert given characters to a 0 and a 1, move it into a set of 8 characters, and then use the ASCII standard, which that ASCII standard is common across Windows, Linux, and Mac OS. Sometimes 7-bit characters are used to represent letters. More commonly today, 8 bits are used. And we can encode numbers, punctuation, spaces, and more. And the only way to convert between these things is to use a lookup table. There's no mathematical approach to it. Okay, so for some additional reading, you have this here. Don't forget, hexadecimal is your pal in this case because it can help you to avoid errors in reading zeros and ones. Thanks very much. Have a great night.